Good morning, students. So this is part 2 of D and F block, class 12th. And the topic I'm going to discuss here is the variation in atomic and ionic sizes of transition metals. So in general, if we compare the ions of a given series, of a same series or same transition series having the same charge, like if we consider all the elements which belong to the same series have the same charge, which is plus 2. So ions should have the same charge. If I compare the size of the ions of the same charge in a given series, you will observe that, or it is experimentally shown that there is a progressive decrease in radius with increasing atomic number. And why it is so? Because the new electrons enters in a d orbital each time, and also as the new electron enters, the nuclear charge also increases by the unity. And this is because of the shielding effect of a d electron, which is not that effective, which is very poor. So because of the poor shielding effect of a d electron, the net electrostatic force of attraction between the nuclear charge and the outermost electron increases. And because the force of attractions between the nuclear charge, between the nucleus and the electron increases, the ionic radii decreases. And the same trends is observed basically in the case of simple atomic, means the atomic radii of a given series, means we are comparing the elements of basically the transition metals or the transition elements in a same series. We compare the ionic size and we compare the atomic size, both follows the same trend, means this atomic as well as the ionic size of a transition metal decreases, because as electron enters into a d orbital each time, the nuclear charge also increases by the unity. And we know that the d orbital shows a very poor shielding effect, due to which it doesn't shield the electrons very effectively. So the nuclear charge, basically the force of attraction between the nucleus and the outermost electrons increases, and thus the size decreases. But the thing is that if we compare the variation of three different series, like if we compare the variation of sizes in 3D, 4D and 5D series, so first two series, they have very much significant difference between the atomic sizes, but the atomic size of 4D and 5D series has no much difference. It is almost the quite similar, right? And why it is so? That the atomic sizes of the elements which are present in 4D and 5D, they almost the same, they are virtually the same. Because there's a phenomenon which is associated, that if we have to fill the 5D series, so before filling the 5D orbitals, we have to fill the 4f orbital. So in fact, the electrons which are present in 4f shell, they also show the poor shielding effect, and because of that, the size of the atoms decreases, or the size of the atoms which is present in that particular series, it starts decreasing. There is a regular decrease, and that decrease is basically known as the lanthanide contraction, because it is in the 4f series, and that belongs to the lanthanoids. So that decrease in atomic radii, it really compensates with the expected increase in atomic size with atomic number. So basically, the atomic size of the 5D series should be larger than the 4D series, and there should be a large difference. There should be large difference, but the difference between the size of 4D and 5D is not much large. It is quietly almost the same. They are virtually the same. And why? Because before filling the 4D, the 4f orbital has to fill, and when the 4f orbital started filling, so what is happening? The size is basically decreasing. So that decrease in size compensates for the expected increase in the atomic size in the next series. So that is why, because of that lanthanide contraction, the atomic size of the second and the third series, they exhibit the similar radii. They have the same similar radii, and because they are having the same similar radii, so they have similar physical as well as the chemical properties. Fine, and it is much more than the expected on the basis of usual family relationship. So basically, now if we talk about the lanthanide contraction, we will discuss in the F block also. But see, the factor which is responsible for the lanthanide contraction is basically the same which we observed in the transition series. Because see, in the transition series also, the d orbital shows the poor shielding effect. In the same thing in the case of lanthanoid. In the lanthanoids, we have to fill the 4f first, and the f shows basically the more poorer shielding effect as compared to the t. So because of the poor shielding effect of one electron by another in the same set of orbital, so shielding is very less. So force of attraction between the nucleus and the outer electrons will be more. Hence, there is a fair decrease in the size of entire 4f orbitals elements. right? So you can see this is a graph, figure 8.3, which is showing the size of the elements belongs to the F block. So this is basically first 3D series. This is 4D and 5D. You can see the size difference between 4D and 5D is not that much, quite large. It is almost the same. But if we compare the size difference of first and the second series, it has the quite large difference. So the decrease in metallic radii, it coupled with the increase in atomic mass, results in a general increase in the density of these elements. Obviously, because the atomic mass is increasing, so generally the density of these elements also increases. So thus from titanium to copper, there is a significant increase in the density, which may be noted, and it is a table 8.2 where the electronic configurations are given, enthalpy of atomization, some of the properties values are given for a third 3D series or the first series of the transition element, which you can read it for your further knowledge. It will enhance your knowledge, or it will enhance the understanding power of basically the topic which I am going to discuss here. Now next is the ionization enthalpy. So ionization enthalpy means energy required to form an ion. Then it is quite obvious when the size is decreasing, the nuclear charge and the electrons, they both shows the increased electrostatic force of attraction between them. So when the force of attraction between them is quite large, so it means they require more energy to remove the outermost electron. So but if we compare the stepwise or successive enthalpies or the ionization enthalpies of these transition elements with the non-transition elements, there is a quite difference. So the successive enthalpies of transition elements, they basically they do not increase as steeply as in the case of non-transition element. And obviously the variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition element. Means if you compare the elements which are in a period and belongs to non-transition, like if you compare the third period, fourth period elements, and you don't compare it with the transition, but if you compare the elements of P block which belongs to third period or fourth period or fifth period, and you look at the ionization values, so there is a steep increase. But the same thing if you compare in the case of transition, there is no steep increase, but in the case of non-transition elements they show steeply increase, right? So why it is so? Basically I will discuss this thing, why it is so that there is no steeply increase in the case of ionization enthalpy in the case of transition element. So the first transition enthalpy in this transition case increases, but the magnitude of the increase in second and third for the successive elements is much higher along a series. Means if you compare the first transition enthalpy, it is fine, it is increasing, it should increase, but if you compare the magnitude, if you compare the value of second and third ionization enthalpy for that particular element, for that successive element, you will see there is a very high difference, it is very high, it is much higher than along the series. So the irregular trend in the first transition enthalpy of 3D series, though of little chemical significance, it can be counted for by considering that, see, there is a lot of irregular trend in the first ionization enthalpy for the metal 3D series. Why? Because we have to remove electrons from 4s as well as 3D, but the electron has to remove from the 4s first rather than 3D. So first the electrons from the 4s has been removed, after that there is a number of 3D comes, fine. So D block elements, they form ions. So when ns electrons are lost, then only n minus 1d electrons will be lost, or 3d electrons will be lost, or 4d or 5d, whatever it is. So as we move along the period in 3D series, we see that the nuclear charge increases from scandium to zinc, but electrons are added to the orbitals of inner subshell. Means if you move from scandium to zinc, electrons, they are being added, and first electrons it will add in 3D orbital, and when the 3D orbitals it get filled, then it will go to the 4s, fine. And if you compare the shielding effect of 3D electrons with 4s, then see the 3D electrons, they shield the 4s electrons very effectively, fine, more effectively, because 3D electrons, they are inner electrons and 4s is the outer shell. Now 3D electrons, they shield the 4s electrons more effectively. So that is why the nuclear charge, and so, because of that, the force of attraction between the 4s electrons and nucleus is not that much large. Fine, that is not quite high. So 4s electrons can be lost easily. So that is why the first ionization enthalpy is not that much large. But once the 4s electrons has been removed, now we have to remove the electrons from the 3d only. Now if you now the electrons which are present in 3d only, now because 4s has now 0 electrons, now electrons, one electron which is present in 3d, it will shield, it will not properly shield the another electron that present in the 3d orbital. Now here the shielding effect is not that much effective, it becomes poor, because the d orbitals, all the d orbitals, they have different directions, so electrons are also in the different direction. That is why one electrons of d orbital do not or does not shield the another d electron which is present in the same orbital effectively, because all the d orbitals, they lie in the different directions. Now the shielding is not very effective, it is very poor. So in that case, the electrostatic force of attraction between the electrons and the nucleus increases, and that is why the value of ionization enthalpy for the second step, for the second ionization enthalpy as well as for the third, if it comes to the third, it becomes quite high or larger value. This shows larger value. Fine. So a general trend of increasing value of second ionization enthalpy is expected as effective nuclear charge increases, because one d electrons does not shield another electron from the influence of nuclear charge, because d orbitals differ in direction. So the trend of steady increase in second and third enthalpy breaks for the formation of manganese 2 plus and 3 plus respectively. So in both the cases, ions have 3-5 configurations, and similar breaks occur at so many elements which is present in the later transition series. Now, so if we interpret the variation in ionization enthalpy for electronic configuration Dn, so interpretation is that the ionization enthalpy's variation basically depends on the three terms. So value of ionization enthalpies, it depends on the three terms. The first is the attraction between the electrons toward the nucleus. Second is the repulsion between the electrons and the exchange energy. Third one is the exchange energy. So on the three factors, the value of ionization enthalpy depends. So first is the attraction between the electrons and the nucleus, second is the repulsion between the electrons, and third is the exchange energy. And exchange energy is basically the main factor. It is responsible for the stabilization of energy state. Now see, if you have half-filled or full configuration, in that case all the possible sets of degenerate orbitals which have same energy, we call it degenerate. All the degenerate orbitals have single electrons, they occupy a single electrons, and at that position the exchange energy becomes higher. Fine, because now they can maximum possible extent of single occupation, they can exchange these spins with each other. So parallel spins are there. So in the case of parallel spins or the full filled or half filled configuration, the basically the exchange energy becomes higher. So when exchange energy is high, the stability is also high. So basically the loss of exchange energy increases the stability. So as the stability increases, ionization becomes difficult. So if we see in the case of if we compare the ionization enthalpy of Mn positive and Cr positive here, you can see this is 3d5 4s1 and 3d5. So it is quite easy for manganese to lose electron from 4s, because 3d electrons, they are shielding the 4s orbital electrons much effectively. But in the case of, if you compare with the d5, if you remove one electron from the d5, it is quite difficult, because now the electrons are in the d only, and d electrons, they shield another d electron very poorly. So that is why the third electron which is being removed from the 3d is very difficult to remove. So now the enthalpy, second ionization enthalpy for chromium positive will become difficult, because, and second factor is that in the case of chromium positive, all the degenerate 5 orbitals have same unpaired electrons. They have they have basically 5 unpaired electrons, which have all the electrons have same spin, they are parallel spins, and the exchange energy is high in that case. Fine, more the exchange energy, more will be the stability. So here the ionization will be high. In the same way, if you compare with the Fe2 positive, which has D6 configuration, and Mn2 positive, which has 3d5 configuration, so here the ionization enthalpy of F2 positive will be lower as compared to the manganese 2 positive, because again 3d5 has the stable or half-filled configuration, so exchange energy will be high here. Right? Now the lowest common oxidation state of these metal is +2, because all these have electrons in the 4s orbital and it is outer lying orbital, so it has to remove first. So lowest common oxidation state of these metal is +2. And to form M2 positive ions from the gaseous state, so we require the first and second ionization enthalpy, also in addition to the enthalpy of atomization. Right? So dominant term in this second ionization enthalpy, which shows unusual high values of chromium and copper, where M positive ions have D5 and D10 configuration. So obviously baat hai, the second ionization enthalpy will be higher for chromium and copper, because in the second ionization state the chromium has D5 configuration and copper has D10, and now the electrons is basically it is very difficult to remove the electrons from the half filled and the full filled state. So obviously they have now higher values of ionization enthalpy. The same thing if you compare with the zinc. So removal of 2 electrons from the zinc will be quite easy because it lies in the 4s orbital, but after removing these 2 electrons, the third electron is not easy to remove, because again it attains the D10 configuration and it is again fulfilled, and very difficult to remove electron from the D10 configuration. Fine. So trend in the third ionization enthalpy is not complicated by the 4s orbital factor, shows the greater difficulty removing an electron from D5 and D10. Fine. So third ionization enthalpy यहाँ पे क्यों बहुत ज़्यादा है? It is not because कि because there is a poor shielding effect. Basically the reason is the removing electron from the basically removing electrons from the most stable electronic configuration, which is D5, which is half filled, and the D10, which is full filled. So here the reason is the stability. Note the 4s orbital factor. So in general the third ionization enthalpies are quite high. And also the high values of third ionization enthalpies of copper, nickel, zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Right. So in general, so basically the exchange energy or the stability of half filled and full filled explains the high value of third ionization enthalpy in the case of copper, also in the case of nickel, also in the case of zinc also. So copper, nickel, zinc, they shows a very high value for third ionization enthalpy because it is very difficult to remove the electron. So although the ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, and this problem is very complex, not amenable to ready generalization. So this is so in this video the two topics has been covered. One is the variation in the atomic and the ionic sizes, and second is the ionization enthalpies of transition metals.